let's look at some electrochemical cells. So I've got one set up here that would have a zinc electrode on the left side and a copper electrode on the right side. And in between there's an electrical resistor, which could be something like a light bulb or whatever we wanted to power using our battery, which is another way of saying electrochemical cell. Now this isn't quite complete because we'll have to have a solution containing some zinc ions over here, and we'll have to have a solution containing copper ions on this side. So let's add that in. So there's our zinc ions, and here's our copper ions. Now, in order for this reaction to work, we'll have to have oxidation and reduction. Now, convention says that we put our anode, which is where the oxidation happens, on the left side, and we put our cathode, which is where the reduction happens, on the right side. So I'm going to go ahead and write anode over here, and I'm going to write cathode over here. Anodes are generally considered to be the negative side, and cathodes would be the positive side. So if you look at a battery, you could see, negative and positive. Such as, here's a AA, or AAA, sorry, and there's the negative side and the positive side. So we could see what kind of chemistry would go on in each case. It looks like this alkali battery is leaking a little bit of potassium hydroxide there, so I'll have to throw this one out. Now we're not quite done with our battery because these ions need to interact with each other. Now I could have put them all in the same solution, but if I did, the electrons wouldn't flow through our wire or through our resistor up here. So that would short circuit, and we need to keep these two halves of the reaction separate from each other. And so we'll do that with a salt bridge. Which is just a tube that has some ions in it, and it may have even like a gel, or it might just be some piece of paper, something that kind of keeps the two halves of this reaction apart. Now let's look at what happens to the flow of electrons. Over here, anodes get oxidized. So oxidation, I'll go ahead and write that. And cathodes is where reduction happens. And sometimes people remember that by saying anox and red cat. So that's a little acronym or mnemonic. Yeah, mnemonic for that. Now, oxidation would mean that we would go from zinc 0 to zinc 2+. That would increase the oxidation number. And reduction would mean I would go from copper 2+ down to copper 0. Now, next we should look at what's actually happening with the electrons, right? So, if I'm generating electrons from here by making zinc 2+, then I'm going to have electrons flowing in this direction. That's why this one's called the negative terminal, because that's where the electrons come from, and then they head towards the positive terminal. Negative charges like to go to positive things. So that flows over here, and then the electrons are available on this electrode, which then will attract these copper ions, which will then add on to this electrode. So the mass of this electrode as our reaction progresses will increase, and the mass of this electrode will decrease as some of the zinc will then be dissolved into the solution. And this is how an electrochemical cell works. And again, we need this connection so that the ions can flow through the solution. Now, inside of this salt bridge, it doesn't actually need to be any of the ions that actually participate in the reaction. It just needs to be something that can carry the charge. A lot of times potassium chloride is used for that, even though it's nowhere near represented in our electrochemical reaction. Now, if we wanted to, we could draw out all of these things, right? Draw the cell out just like it looks here. But that can get cumbersome. And so there's actually another kind of way of representing what we've drawn here. And that's called line notation. And what we do is we start at the anode and then work our way through the salt bridge and then over to the cathode, and we'll separate all of the times that we go from one phase to another with a line, and we'll separate, or we'll represent a salt bridge with two lines. So our line notation will look something like this. Our zinc electrode, you always start with the electrode of the anode. And then there's a phase difference between this. This is a solid, this is dissolved in the water. So there's a line for that phase difference. And then we write zinc 2+, which is aqueous. Now, you could also, in the middle of this line notation, say how concentrated this solution is with the zinc. But for now, let's just keep it simple and just say, here's the zinc solution. Now we come to our salt bridge, which is represented by two lines, just like this. And then next, we have our copper solution, because that's what the salt bridge is in contact with. And then finally our copper electrode. Right there. So that's an example of using an electrochemical cell and translating it into line notation. Now, you may wonder what happens if we have more than one thing in solution at a time. So let's have a different cell. I'll just quickly draw that here. Let's say that instead of having a copper wire here, we have a solution which is iron 3 and iron 2. And then we have another solution over here just so that we can complete our electrochemical cell. This one will have a piece of silver and we'll have a solution of silver. Now, over here, the reaction is actually between iron 2 and iron 3. And over here, the reaction is between silver metal and silver ions. Well, with silver metal, this is something that can conduct electricity. I can easily clamp onto it, and that's fine. And this is an example of what we would call an indicator electrode, which just means that the electrode will participate in the reaction. And so in this case, silver and silver ions, the reaction will be between silver and silver metal, the ions in the metal. Over here we have a reaction between iron 2+ and iron 3+. Both of these are dissolved in the solution. So I'll need some metallic substance or electrical conductive substance over here to allow the flow of electrons through here. And one of the things that I can use for that's typical is a platinum electrode. So I'll just add a platinum electrode over here to this solution. platinum. And then we've got our rest of our electrical circuit, and of course we'll have our salt bridge in the middle there, ready to go, so that we're connecting both of these solutions. Now again, I've chosen to put the anode on the left side and the cathode on the right side. And so what will be happening over here is oxidation. So we'll have iron 2 plus being turned into iron 3 plus in here. This electrode is inert. It's not changing during the course of our reaction. And then over here we'll have reduction. So our silver will be plating onto the electrode. So adding mass to the electrode, growing its size. And if we were to look at line notation of this, we would start with the electrode over here, which is a platinum one. We could have put something else here, but we want something that won't react directly with this metal, and platinum is something that will do that. Another good choice for that is gold, or if you want to choose something that's a little less expensive than either of those things, some people will use a carbon electrode because graphite or something like that can conduct electricity. And indeed, if you open up some of the, like a D-cell battery or something, you'll find that generally it'll have a carbon electrode in it, not a platinum one or anything like that. Something about wanting the batteries to be inexpensive. So we have a platinum electrode here, and then we have two things in solution. So we just write the two things. Fe2 plus, which is in solution. Put a comma, next thing in there. Salt bridge, and then the cathode solution, or side. Just like this. So, and again, we could have denoted how concentrated each one of these ions is in the solution, and that'll be important for later. Now, so far we've had electrodes interacting with something dissolved in the solution, but we can also have them interacting with a gaseous substance. And I'm just going to sketch this one side of this electrode just so that you can see what the line notation for that would look like. So again, I'm going to choose a platinum electrode, and then I'm going to draw all these little bubbles around here, and somehow we're bubbling hydrogen gas through here. Maybe there's some kind of tube. I didn't really leave myself much room there, but there's a gas tube that's bubbling hydrogen up through here. I'll put a little hole in the bottom of the flask here. It's going in, bubbling up around the electrode. And then in the solution, there's a solution in here. We have hydrogen ion, so H+, acid. Now, if we want to write the line notation for this, which happens to be a standard hydrogen electrode, this particular one has a name, we'd have platinum, solid, interacting with H2 gas, and then phase change, because this is a gas, this is aqueous, so we have phase change, and then hydrogen ions, and then we would have our salt bridge, and then whatever other electrochemical cell I wanted to put over here. So that's how to look at an electrochemical cell and hopefully translate it into line notation. I'll probably be switching a little bit in between these two, but I find the line notation is fairly convenient because it takes a little bit less time and a little less space to do.